Second, and I will start sharing my screen. Okay.
So, good morning or good afternoon, everybody. My name is Tobias Nipko. I'm sharing this session, and we will have two talks, one on hardware and one on software verification. And we start right now with the talk on hardware verification by Vedat Hadžić.
Yeah. So should I start right away, right?
Actually, I think there's a minute left, so I was a bit too proactive. Starting now.
So hello everyone and welcome to my talk on proving CIFAR protection of masked redundant circuits. My name is Vedat Hadžić, and this has been a collaboration with Robert Primas and Roderick Bloom from the Graz University of Technology. So the motivation behind this paper is that we have all of these circuits that do some computations, and we want to protect them against implementation attacks. So whenever you have a system, an attacker is trying to kind of get credentials or extract some secrets, some secret keys from the circuit and so on. So there are two kinds of implementation attacks that we are mostly worried about, which is a passive implementation attack such as power analysis, where an attacker is able to take your circuit, measure the power consumption, and then try to correlate this power consumption to the data that is being processed by the circuit. And this way, like through sophisticated statistical analysis, an attacker can guess which secret key your computation used. And the other type of attack that we have to protect against are active attacks. An example of this are fault attacks, where the attacker messes with the design in some way. For instance, shining a laser on the chip and then introducing a bit flip at some particular gate in the design, making the design compute the wrong things. And then from observing what kind of wrong things the design computed, the attacker can retroactively figure out what the secret must have been before messing with the circuit. And we have quite powerful countermeasures against this. So the power analysis attack can be thwarted by using masking, and the fault attacks can be thwarted using redundancy. So by introducing masking or redundancy in your circuit, you should be able to protect against these attacks quite effectively. However, although it was long believed that combining both of these should give you a design that is secure against both, you actually have the situation that these countermeasures don't play along really well. So recently, there has been another proposed attack called statistical ineffective fault attack that requires these two ingredients. So it requires masking and it requires redundancy, and the attacker is still able to somehow infer what the secret data was that your circuit was computing with. And the main idea behind this paper is, can we create a tool or an algorithm that can automatically prove for any given circuit whether it is CIFAR resistant or not? So if it's CIFAR resistant, we would like to have a certificate that it's resistant, or if it is vulnerable, we want to have a location at which we need to introduce a fault to kind of test this in experiments. So the contributions of this paper are such an algorithm. So we have managed to create an algorithm that proves CIFAR resistance. we have evaluated our implementation on very interesting S-boxes that are used in practice, such as the Ketchak S-box, 4-bit permutations, and the AES S-box. And we provide secure Verilog S-box designs at the end. So let's go over some background so everyone's on the same page. Masking is a countermeasure for power analysis where we try to break the power correlation. And the way people found this is possible is to just go ahead, take each bit of your secret data that you're computing with and split it into several shares. So you do this by splitting it into two parts, for example, that as an XOR give you the original result. So X is equal to X0 XOR X1. What you also need to make sure is that your shares are uniformly randomly distributed. And you do this by having a random number generator picking a bit and then taking one share as the secret bit itself, XOR the random bit, and the second share as the random bit. And what you need to make sure is you rewrite your whole computation, your whole circuit in a way that you never combine these two shares so that an attacker that observes power could not correlate it back to the secret. And one popular masking scheme is called DOM. And here I'm going to give you an example of how this looks like. So let's say that we want to create an XOR of two bits A and B. They are split into shares A0 and A1 and B0 and B1. And how we do this XOR is by just taking both of these share parts and then XORing them individually. So this is pretty simple. This is the easy part. However, for nonlinear gates, such as the AND gate, it gets much more complicated. So you have to do a bunch of Boolean algebra, which I'm not going to go into. But essentially, you create the cross product and then you XOR the terms again to get two shares at the end. Importantly, you have to introduce another fresh random mask into the circuit because otherwise the intermediate results would correlate to your secret. So this is kind of an overview. And let's look at redundancy as well, which is a fairly simple concept. Just duplicate your circuit several times and then cross-check the results. So in this case, we have a circuit F that was duplicated into two copies. And then you take the outputs of each copy, XOR them to see if they're different, and then report an error value delta if they are different in any single bit delta 0. So how this works is an attacker introduces a fault. This will have to affect one of the outputs. And if one of the outputs is different, you report an error. So let's see how these two interact and why this SIFA is possible, so the statistical ineffective fault attack. So we start with a masked circuit. This is the circuit from before for the AND gate. You duplicate it, so you create a second copy. Because I will not need the whole circuit in this example, I will remove some parts of it. They're obviously still there, but not shown. And we have this error detection value delta. And if under normal computation, if there is no fault, then this delta will always be equal to 0 because you're XORing two things that are identical. But let's say that an attacker is able to flip this A1 in the right copy to a not A1, so introduce a bit flip. This bit flip propagates through the right half of this circuit. And we see that the terms that it computes are different, and the final value of delta is given as this gigantic term of XORs. If we look at it more closely, we see that A1 and B1 XOR not A1 and B, A1 and B0 XOR not A1 and B0. When you simplify this down, you get B0. For the second term, you get B1. And the masks M kind of evaporate. So finally, as a result, you have that the detection value delta is equal to one of the secrets. And this is really bad because the attacker can just make a fault here and then observe delta, so observe whether the error was detected or not. And from this, figure out whether B was 0 or 1. So this kind of bypasses the whole masking thing, and it, like with faults, you can bypass masking, which is really bad. So one of my colleagues, Robert, figured out a way of doing this in a way, so creating masked circuits that are CFA resistant, and it's really clever. It uses technology from like 40 years ago called reversible computation, where you have a circuit that is always invertible. And if the circuit is invertible, they have shown that if you make a bit flip at any point in the circuit, it will always propagate to the outputs, meaning that you can never get an ineffective fault. So this is the theory behind why CFA resistant circuits are possible. And this is a better proposed design than the one that I've shown you previously that was vulnerable. So the big question in the room is how can we check whether this new circuit that we mask with this sophisticated masking scheme is secure? Because first of all, as we all know, developers can make mistakes, which lead to many, many vulnerabilities. And also, compilers can mess with the design. So as soon as you write something in a higher level language and you compile it down into more basic languages, it messes with the design in very subtle ways that can make it insecure. And therefore, we need a verification method. So we need an automatic method where you just plug in the circuit and it tells you secure and not secure. It gives you kind of an idea about the security, and it also gives you the location of the vulnerability if it's not secure. So we created such a verification method, and the attacker model looks like this. So the attacker is able to create a bit flip at any point in the circuit at some gate. So as we have seen before, we had this input gate A, and the attacker was able to just flip the value to the negation. So this is the model that we use in the paper. And the proposition of the whole paper is if a computation with a fault detection value delta is CFA resistant against a fault-inducing attacker, if delta is statistically independent of all secrets. So if we can show that for each single fault location, delta is always statistically independent of all secrets, then an attacker that observes delta will only observe garbage. So they might observe some values that are changed between 1 and 0, but they will never statistically be able to infer a secret. So we devised 3 different heuristics that we used in this paper to show this. And the first one is incompleteness. So if delta is functionally independent of at least one share, it cannot leak the secret. And we can test this with SAT solvers quite efficiently. So this is the usual dependency test where you take one copy where you set it to false and take one copy where you set it to true and then see whether this is not satisfiable. The second property is hiding, where we figured that uniformly random values have this nice property that they can hide secrets because of their uniform randomness. So if we can factor delta into an expression mask x or delta prime, where that delta prime does not contain the mask, then we have shown in the paper that delta cannot leak the secret. So the mask n kind of hides all secrets that appear in delta. And this can be checked again with this formula. So you set m1 to false and 1 to true, and you check whether this can ever be equivalent. And if the result is unsat, then this factorization is indeed possible. And the last one is the trickiest, which we called inferred independence, where we say if all linear combinations of delta I do not leak secrets, then delta does not leak secrets. And this has a quite complex proof, and it relies on the structure of delta, because delta is this gigantic OR over these single detection values for each output. And if you take the all linear combinations of those and show for them that they're independent of the secrets, then delta is also independent of the secrets. What? And all of this can be checked recursively. What's happening? Hello? Okay. Something strange happened with my slides. I'm sorry. But yeah, we use this method to kind of divide the circuit into smaller parts and check the security of each of these linear combinations. So the summary of the algorithm is check for incompleteness. If it's incomplete, then it's secure. Try to factorize uniform random values. If you can factorize them, then it's secure. Or otherwise create a basis of all subfunctions and then test the properties recursively. This is pretty much the whole algorithm for testing this. And we tested it on some case studies. So the first case study was this Kechak G3, which is a 3-bit SBox, and we implemented it with Robert's genius design with reversible gates. And then I expected that the verification tool is just going to say, okay, it's secure. But alas, the tool reports an implementation is insecure. So the tool was not able to prove security. And it turns out that the bug was in the way the synthesizer was used. So the synthesizer just threw away my whole like nice design and reused some gates to make it smaller, because that's its job. So the compiler tries to make it as fast as possible and as good as possible. But because it reused these gates, it essentially meant that by introducing one fault, you could affect 2 different gates, and this broke the whole design. So the conclusion of this kind of case study was that you cannot trust your tools. So as soon as you use a synthesizer, you cannot trust the output that it produces. You always have to check it again. And the results were interesting. So for the correct design that we got at the end, we managed to prove this in like under a second. And for all the other designs, we were quite quickly able to say, okay, we are not able to prove this. You probably have a bug at this location. And let me note that in every single case where the tool said that this location is vulnerable, it indeed was. So we tested this also empirically. So then new idea. Let's implement everything by hand. I will not trust any synthesis tools ever again. So I did that. I removed this intermediate step of compilation and made the netlist by hand for this circuit. And then the tool reports, okay, it's secure, very good job. And essentially we have proven that CIFA was not possible in this case. So this gave me a bit of confidence that I can make these designs by hand. I don't need any synthesizers. And we managed to again show the security in under a second for all of these. But then we came to a much bigger design, which is the AES SBox, like the pinnacle of complexity for SBoxes. And then I thought to myself, okay, I'm again going to implement it by hand. However, it turns out that this is orders of magnitude larger than anything I've ever looked at before in these experiments. So it's much larger, like 10 times larger than the largest one that I've looked at before. And it's much more complex because of the nonlinearity of the SBox. And then the tool reports insecure. So I implemented it by hand, tool reports insecure. which means that the user did something wrong. So this design is obviously wrong, and it's wrong in a bunch of places. And then what you can do is use the tool iteratively to figure out, okay, this location in the circuit is vulnerable, this location in the circuit is vulnerable, and like handle yourself through the circuit until you find all the locations and then show that it's secure in the end. So like iteratively removing all of these bugs until the tool finally says that it is proven that CFA is not possible in this circuit. So yeah, you can use it for development purposes as well, not just to test the final design. And it was a bit slower in this case. So each time that I made a mistake, it was able to detect it. And you see that the location of the fault kind of it influences the duration of the verification. So if the fault is sooner in the circuit, so in the topological order of the circuit, then it gets found quicker. And if it's later, then it gets found much later. But in the end, we still managed to prove that this final AES S-box design was secure in like 184 seconds, like about 3 minutes, which is quite quick and usable for development purposes. So as a conclusion, this is the first verification method for CFA resistance that can be applied to general circuits. We provide an implementation that does this. The tool is called Danira. And we have successfully secured many interesting S-boxes that people use in practice. So Ketchak S-box, all classes of 4-bit S-boxes, and this gigantic AES S-box. So thanks everyone for the attention, and I will take questions now. Did I go over time? I hope
no, you
not.
didn't. Quite the opposite. I did not go over time. I just messaged you that you have 5 minutes left.
So okay.
So the floor is open for questions. I have a question concerning the the statistically. I didn't see any statistics. Where do they hide?
Yes, that's a good question. So the thing is, so what the attacker is trying to do is to like observe this error detection value many times and then infer, like, let's say that we have this example from here where delta is equal to B. Then the attacker, by observing many of these executions, would be able to kind of go back and do a statistical analysis of the results of when does it give me 1, when does it give me 0, and go back to computing B. So what we do is we show that this statistical dependence is not possible, and we do it in a kind of roundabout way. So like we try to show it with these heuristic properties. So functional independence of the shares implies statistical independence. Factorization of a mask implies statistical independence. And then independence of all linear combinations again implies statistical independence. So it's kind of hidden. It's because for doing it in a, I mean, what you can also do is you can do it exactly. So we did it with heuristics because they perform a bit better than exact methods. So what we did also for the paper was like take one of these exact tools. In this column, it's the S column. This is an existing tool that we kind of heavily modified to do this essentially look at all the truth tables and see whether there's a statistical dependence. And I didn't want to go into it in the talk, but the heuristical tool is much better than the exact tool that looks at the truth table and does this exact calculation. So here we see that it's like, I don't know, 10 times or more, 15 times faster than the exact tool.
So is it fair to say that the main contribution then are your heuristics?
I mean, the heuristics are somewhat inspired by other literature that we have on masking verification. I would say that the main contribution is the first method that does this explicitly for CIFA, and the first CIFA secure designs. So in this paper that one of my co-authors had, where they proposed this reversible computation method, they kind of said, okay, and if you do it like this, then you're going to have secure designs. And I wanted to have some secure designs, so I followed their instructions in the paper very, very carefully. But it turns out that either you mess up or the synthesis tool messes up and so on. So in reality, these are the first implementations that are secure against CIFA, and they're proven secure against CIFA.
Thank you.
One thing is to have, in theory, an algorithm that is secure, and the other is to have an implementation that's also secure.
Further questions? Don't be shy.
I have a quick question.
Yeah.
When implementing the AES box by hand, was this location identification also helpful in this case, where the gate
Yes.
that a circuit is really larger?
Yes, it was. So what it does is, so the way you implement this AES box, it's based on the Kentwright AES box, which is like a design that uses many sub-circuits. And what it turned out that I messed up in one of the sub-circuits, and you can identify the exact gate where this happens. So you can go back to, what I did was I wrote myself code that generates the S-box. I didn't do every single gate by hand. That would be impossible. But what I did was I created a generator for the S-box that uses exactly these reversible computation gates. And it turned out that it found the locations quite efficiently. So it found the exact first location where I messed up. Then I went back into my generator for the S-box, and then I looked at the part that generated it, and in every single case, it turned out that I inadvertently created a copy. Instead of creating a copy of a gate, I reused the same one. And it was super helpful. So it took a long time to get this S-box working. I think a week until it was implemented without any, and without the tool, I would have never been able to do this. So I think it's quite necessary to do this checking during development, especially for something that has it's kind of a hyper property. It's not exactly okay. When you do this, then it's supposed to give you this exact result. So it's more of a structural kind of thing, where the structure of the resulting circuit is very important. So yeah, it was super helpful. I could have not done it without this.
Okay, cool. Really cool. Thanks.
Yeah, thanks for the question.
I have a naive question. In the end,
yes.
I mean, you kept modifying your design, but in the end, I assume you also proved functional correctness.
Obviously, yes. I mean, it was, I tested functional correctness all the time. It's much easier. You just have 256 values that you have to put through the circuit and check the result. So this is the very simple part. The hard part was getting it working with CIFA.
Yeah, because it's only.
But yeah, obviously you have to check functional correctness all the time. And for these kinds of designs that are like just permutations of the input domain, it's quite simple as long as they're small. So S boxes are typically 8 bits at most, so you can exhaustively check them.
Okay. So I think that brings us to the end of this session. Thank you very much for your talk.
Yeah, thank you.
And we move on to the next talk. Now it's about software verification, or more abstractly about monitoring or enforcement of hyperproperties. And we move from Graz in Austria to Saarbrücken in Germany. So Christopher Hahn is going to give the talk.
All right, thank you very much. All right, can I see the slides?
Yes.
Perfect,
Yes.
Thank you. All right, I'm really happy to present joint work with Noreen, Bernd, Jana, and Yannick, which is on runtime enforcement of hyperproperties. And I would like to start by giving you a brief intuition on what hyperproperties are and why they are so interesting. So one example domain where hyperproperties occur very frequently is in security, and especially in information flow control, where one is interested to avoid that information leaks from high security input, such as credit card information, to the public domain. So in this example here, for example, it is not the case that we are just directly writing high security inputs into observable outputs, but it's more the case that this information leakage is very implicit through the system. For example, by the possibility of an observer to observe multiple computations of your system, and then by identifying differences in those computations, one can then might infer something about secrets. So in this case, there are the observable inputs to the system are the same, but the observable outputs in this example are different. And by observing those differences, one can gain information or knowledge about a secret. And what's so special about hyperproperties is now that you cannot look at a single execution trace in isolation, but you have to actually relate runs of your system to each other. And hyperproperties occur very frequently in today's systems. So for example, in symmetry in protocols, where you're interested in that there is a symmetric execution when swapping parties, for example, or a very hot topic in robustness or fairness in machine learning, where one is interested that, for example, if the inputs into your machine learning model are sufficiently close to each other, then the outputs of the machine learning or the predictions should be sufficiently close as well, so that there is no discrimination, for example. And there are many more examples, error-resistant codes, bound determination, linearization, and many more. And what I would like to argue in this talk, and what we argue in this paper, is that getting such hyperproperties right, and getting, for example, information flow right in a system is very tricky, especially if the system is large. Every new line of code can introduce more problems and more leakage, for example. And we would like to argue that we could outsource the check and the verification of a reactive system that runs continuously to an enforcer who does this checking at runtime. And then not only checks if a hyperproperty is fulfilled, but also corrects the implementation. So for example, if an enforcer detects that the output of or the predictions of your model are not sufficiently close, it could fix this during runtime. Or if the enforcer detects an information leak, just stopping the system is not enough, because this would also leak or introduce a leak as well. But you have to continue somehow with the system. And by doing this, you have to make sure that there is no information leakage. So this is what we are doing in this paper, and what I would like to present to you today. So and basically follows this outline. So we will take a look in the first part on the setting that we're into. So we are taking a look at reactive systems that continuously interact with the environment. And we are looking at, first of all, actually on how we obtain multiple traces during runtime to compare them. And we'll take a look at the specification logic in which we are writing our properties, or formalize the properties, the hyperproperties in. All right, so first, I would like to give you an intuition on what runtime enforcement is for trace properties. So the idea is that you wrap your reactive system with an enforcer who just observes your system during runtime, observes the execution trace, and if there's no problem, then it just continues and just observing. But if there is a problem, so if there's something that should not happen, then the enforcer has to take over by computing a strategy such that for every upcoming input sequence, the enforcer can now react with the correct output. So the enforcer has to actually intervene and correct the system. And now the trouble is, by doing this at runtime, is we have to somehow compare traces. So there has to be in somehow models on how we actually get more traces during runtime. And so we are studying, and also in the literature, there were studied two trace input models. The first one is the parallel model, which, for example, secure multi-execution is one of the instances of this model, where you copy your system multiple times and then observe basically a tuple of traces. And the idea here is that the enforcer can alter those traces at exactly the position that we are currently looking at, but it can alter all the traces on those positions. But the important thing is here, which is indicated by this red line here, is that we still have to relate traces, and we are interested in the relation of those traces. And a little bit more of a sophisticated model is the sequential model, where we're actually looking, and you can think of this as sessions. So we have basically, for example, looking at an execution of a day or so, and then in the next day, we start the next session. And the enforcer here is only allowed to alter the session that we are currently into, and especially the position that we are currently into in the current session. Because the enforcer, for example, cannot travel back in time and alter something yesterday or so. So this is a little bit more of a sophisticated model, but it's important that we are still interested in relating the sessions to each other. And by having now the traces in place, I would like to talk about how we actually write down hyperproperty specifications for constructing enforcers. And there is a recently introduced temporal logic for that, which is called hyper-LTL. And the idea is it is an extension of LTL with explicit trace quantification. So you can quantify over traces explicitly by stating something like for all pi, and then index atomic propositions in your logic directly with the trace variable. And so, for example, we can now formalize observational determinism from the introduction, where for all trace pairs, pi and pi prime, if the observable inputs are the same on those two traces for all positions, then those traces should also agree on the observable output, such that something like this does not happen. So, and an hyper-LTL formula gives you now a set of sets of traces. So it's a lifting from trace properties to hyper properties. All right, so yeah, now having set up, we can now talk a little bit more about actually the features of a transform of an enforcer and algorithms to automatically construct enforcers out of specifications and what they should actually do. So on a high level, the features of an enforcer for hyperproperties should do the following. The enforced system should be correct, I think, which is pretty obvious. But another thing, which is called transparency, is that the behavior of the system should be modified in a minimal way. Meaning that if the system does something correct, you just have to let the system run until the latest point for intervention. And the idea now of the next few slides is to formalize this a little bit more, more formally, to being able to construct algorithms that exactly do that and satisfy that. So, and for this, I would like to talk about prefixed strategies, because what an enforcer actually has to do is it has to compute a strategy, so meaning it has to react with outputs to given inputs. And in the parallel model, this means the enforcer has already looked at a given prefix, and then there's this position where the enforcer is into, and then there are the remaining traces that the enforcer has, or the remaining positions of the traces that the enforcer has to observe. And in the sequential model, it is, I think, intuitive that there is one session, for example, yesterday, and then there is the beginning of the actual session that we're into, and this is the prefix that the enforcer has looked at, and there are much more sessions to come. And we can, and the prefix strategy is now a higher order function that exactly matches this intuition, where we are given in the parallel model a prefix, so basically a finite, so a tuple of finite traces, and then given a tuple of input sequences, we have to answer with a tuple of output sequences. And the same idea holds here, given a prefix, or given previous observed sessions and the current session, or the finite prefix of the current session, we then, and this is the difference here, just get one input sequence, and we have to answer with one output sequence. So, and having those prefixed strategies, we can now talk a little bit more about what is, when actually a strategy does something wrong and a strategy does something right. So a losing prefix strategy and a winning prefix strategy. And the losing prefix strategy is just that given a prefix and a hyperproperty, a strategy is losing if there exists some inputs that can occur such that this complete set is not in the hyperproperty. And the same holds for the sequential model, where the set is not in the hyperproperty. And the idea is then that a prefix strategy is winning if it is not losing. All right, so now we can come back to the features of an enforcer for hyperproperties. So the first one was that the enforced system should be correct, which is soundness. So enforcer is sound if for all reactive systems and all input sequences in a trace input model the set of traces that is then produced by the enforcer must comply to the hyperproperty, so is in the hyperproperty H. And a little bit more involved, but yeah, the idea is the same, is transparency. We require that the behavior of the system is modified in a minimal way. So the idea is, if we have a prefix produced by a reactive system with a given input sequence, then if this prefix is winning, then for any prefix that the enforcer computes, this must be a continuation. So the enforcer is not allowed to rewrite a given winning prefix. All right. So having this in place, I would now like to show you how to construct such enforcers automatically. So, and we will first take a look at the parallel model. And the idea is, and what we also do in this paper, is to restrict ourselves to the universally quantified fragment of hyper-LTL, which is basically because having an exist in your formal introduces some of an hyper-liveness property, meaning that this is not enforceable or not even monitorable at times. So we are restricted to this fragment for now. And as input, we also have a reactive system. And the idea is now to, and this is a really crucial part to making this work, is to a priori construct a parity game, which we can use during runtime. And the idea is, since we have a tuple of traces, we can actually encode this as an LTL formula, which basically talks about tuples by replacing the trace quantification just by an indicator which indicates on which trace this atomic proposition was enabled or disabled. And with this, we can just use standard translations from LTL to parity games. And then the idea at runtime now is to monitor for realizability by moving through this parity game. So we're interested in intervening at the latest point in time. So we just move through this parity game. And as long as we are in a winning region, which is here on the left, everything is fine and we don't have to intervene. But if we are an input would move us to, an output would move us to the losing region, which is here on the right, then the enforcer has to intervene. And the nice thing is that during runtime, this parity game arena gives you the strategy on how to react to every given input, every upcoming input sequence. And this is basically the idea, and which is nice that most of the work is done a priori. And now for the sequential model, there's unfortunately, we could prove that for this sequential model in general, the problem is undecidable to construct, to see if a hyper-LTL formula is enforceable. And this can be done by a reduction from the hyper-LTL realizability problem, which is already known to be undecidable in general. But to be fair, this is a really powerful trace model, which looks unbounded in the future. So what about a little bit more of a practical model, which is just finishing the current sessions of the current day. And then anyone at the end of the day could look at log files, for example, fix bugs, and we can restart the system on the next session, for example. And this is possible. And the idea is here, and this is the complete algorithm, but the idea is here to also use a similar reduction as in the parallel model, since we are now, as you can see, it's now a little bit more well-behaved. But we also have to encode the traces of the previous sessions that we have seen so far, which is important part is in line 5 and line 9 and 12, where we have to make sure that we take the other sessions into account. So this brings us to part 3, where we also conducted some experiments, and I would also like to talk a little bit briefly about the merits and limitations of this approach. All right, so for the experiments, we implemented an enforcer for the universal hyper-LTL formulas in the parallel input model based on Strix and PG solver. And we conducted 2 experiments. So the first is enforcing symmetry in a bakery protocol implementation, and the second is enforcing observational determinism. And it started with the first experiment. And the idea of the formula here is that for all 2 traces, the program counters of 2 processes should be symmetric as long as they are selected symmetrically, which is stated here, and the symmetry break, so that a tie break is also symmetric. And we looked at the bakery protocol with implementation with 5 inputs and 46 outputs, and the time to compute the parity game took us 313 seconds. And then what I would like to show you in this table here is that things during runtime are really fast. So when just simulating random traces, this which is a bug in the protocol implementation, but which does not occur by just sampling random traces, but by making sure that this actually happens, where the enforcer has to intervene 10 times in those in those experimental results, and things still remained really, really fast during runtime. So the intervention, just by moving through this parity game, does not cost very much during runtime. So, and for the second experiment, we generated traces where at each position, each input and output bit was flipped with a probability. So by either 0.5% or 1%. So and this led to a lot of instances where the enforcer had to intervene. So we just scaled this up to see if this still behaves, or if it still is very fast, which it is. So this is what you can see on the right side of this table. But what I would like to mention here is that when we scale up the benchmark size, especially the number of inputs, number of outputs, then the initialization time, so constructing the parity game, solving the parity game, really takes a long time and becomes infeasible when increasing this benchmark size even more. So and with this experiment, which is important here, that we identified what the bottleneck is, which is not surprising, because we are tackling here a very hard realizability problem. But which is good to know what the bottleneck is. And this brings me to the merits and limitations. So the current bottleneck is the parity game solving, but which has been, there is a lot of progress which has been made recently. So I think there is still things to come, and which is also a limitation for now, is handling specifications that include hyperliveness. So it's not obvious on how to incorporate existential quantification into an enforcer. And which is also interesting to note is that the enforcer prioritizes the hyperproperty over other functionality. So if you want to have preserve other functionality, you have to encode it into the specification of the enforcer, which of course makes the specification larger and more complicated to solve the parity game. But at the same time, I think this is really a merit, because if you are in a setting where you just care about a hyperproperty, just care about information flow control, specifications can be kept really, really small. and the reactive system can be treated as a black box. And what I think is really cool is that the majority of the workload can be done a priori. So during runtime, it basically costs nothing, since all of the work has been done beforehand. And what there was not enough time to talk about this in this talk, but the complexity drops also when looking just at safety specifications, because then instead of solving a complete parity game, one could construct a safety game, which is cheaper, and solve this game a priori. All right, so this concludes this talk. So I showed you what an enforcement setting for hyperproperties in different input models looks like, and then I showed you explicit algorithms based on parity games for universal hyper-LTL. And I think that the experimental results are encouraging when looking at runtime, and we identified really what the bottleneck is. And yeah, if you're interested to check it out, there is an implementation available. And yeah, I really think that enforcement could be a good sweet spot between like those heavyweight verification techniques, which might be, are infeasible for hyperproperties, and lightweight monitoring, which gives you no guarantees, but just detects errors. All right, thank you.
Thank you for your presentation, and the floor is open for questions. And we've got plenty of time.
I have a quick question regarding the whole idea of this enforcer. So to me, this sounds somewhat similar to what Bettina Könighofer is doing with the whole shielding idea. Is this at all related? And if yes, how?
With shielding, do you mean the safe reinforcement learning via shielding?
Not really. I mean shielding, so synthesizing a small circuit that kind of takes over the control of the outputs if the real circuit is misbehaving or having a bug or.
Yeah, I think.
Yeah, so,
I mean, I'm familiar with this paper on shielding for reinforcement learning. So I think it could be probably the same idea. So I think if you call it a shield or an enforcer, I think it's basically the same. Where here it's I think what the contribution here is that since we are not having just one execution where the shield can immediately be plugged in, but we have to somewhat enforce or shield or whatever we would like to call it against relations. I think this is interesting
okay.
here. Yeah.
Okay, yeah. Makes sense. I'm not sure shields relate different executions to each other.
I think that.
So they could, yeah.
Further questions?
Okay. And another thing I wanted to ask is what the representation of this enforcer is in the end. So after you solve the parity game, is this a circuit or is it like how does it look like?
It is a circuit. So
okay. Thank you.
Sure. Thanks for the questions.
Any more questions? Then I think we've come to the end of this session, and I would like to thank both speakers for their very lucid presentation. And I think because there's no third speaker, this is simply the end, and have a good afternoon or good morning and, of course, further sessions.
Thanks. Bye.
Bye.